find the gradient field for the following potential function. So we have phi of x, y, z here. So we know that we're going to need to find three partial derivatives. And I'm actually going to start here by rewriting this given function to get it ready for differentiation. So we have phi of x, y, z, and we know that this square root can be converted to an exponent of 1/2, and we want to bring that to the numerator, leaving us with x squared plus 3y squared plus 2z squared, all raised to the negative 1/2. So now we are ready to go ahead and find the first order partials. We want to find the first order partial derivatives with respect to x, y, and z. So we need to use the chain rule from Calc 1 to differentiate in each case here. So we have d phi dx. So we're holding y and z constant. So we apply the chain rule and we have negative 1/2. Hold that inside constant. So that's x squared plus 3y squared plus 2z squared. And raised to the minus 3/2 multiplied by the derivative of the inside with respect to x. And so we want to simplify a little bit here. We see we have the 2 in the numerator and 2 in the denominator will cancel each other out to 1, leaving us with minus x squared plus 3y squared plus 2z squared. And that's all raised to the negative 3/2. So we want to do the same thing now for the partial derivative of phi with respect to y. So again, applying that chain rule, I have 1/2 multiplied by x squared plus 3y squared plus 2z squared, all raised to the minus 3/2. And now this is multiplied by the derivative of the inside with respect to y. And again, we can simplify here. We know that 2 goes into 6 3 times, leaving us with a beautiful final answer of negative 3y multiplied by x squared plus 3y squared plus 2z squared, all raised to that negative 3/2. And last but not least here, we have the partial derivative of phi with respect to z. And again, applying that chain rule, we have negative 1/2 multiplied by x squared plus 3y squared plus 2z squared, all raised to the negative 3/2, multiplied by the derivative of the inside with respect to z. And simplifying, we know 2 goes into 4 2 times, leaving us with that beautiful final answer of minus 2z multiplied by x squared plus 3y squared plus 2z squared raised to the minus 3/2. And I'm realizing now that there was a boo-boo up here. I forgot about x in that first term, so make sure that you add x. Minus 1 off my test. Okay, so now that we have the three correct partial derivatives, the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z, we're ready to define that gradient vector field. So the gradient field and that's vector capital F defined by the gradient of phi. So we have our components d phi dx, d phi dy, d phi dy, and d phi dz. So this is going to leave us with, let's give ourselves plenty of room. We have minus x multiplied by x squared plus 3y squared plus 2z squared raised to that minus 3/2. We then had minus 3y multiplied by x squared plus 3y squared plus 2z squared, again raised to the minus 3/2. And then last but not least, we have the z component minus 2z multiplied by x squared plus 3y squared plus 2z squared raised to the minus 3 halves. Again, there's nothing wrong with this answer except that it's rather large. So to make this look a little bit nicer, we can factor out our greatest common factor here, this radical, to the front, and say that del phi is defined as x squared plus 3y squared plus 2z squared, all raised to the minus 3 halves, multiplied by the vector with components negative x, negative 3y, minus 2z. And you can play around with different forms of this answer. We could pull the negative out. We could make that exponent positive. I leave it up to you to have fun with your final answer. And here is mine.